Alrighty, this is a pretty common traffic modeling problem. From our hyperbolic conservation law, we find a PDE for traffic density rho, and we're going to suppose that the initial traffic density rho is given by some function of space alone. So we can say that maybe this is cars stopped at a red light. So we've got some density like this, for example, x equals 0 at the red light. Right, so we might have this type of initial density. We might have a different type of initial density. Suppose we've got light traffic, from the countryside driving into the city. We've got low density on one side. X equals 0 is the boundary between city and country. And then all of a sudden you hit a traffic jam. You hit heavy traffic. Right, so these are a couple of different initial conditions that you might study the evolution of. So what we're going to do is we're going to use the method of characteristics to attack this equation. So let x be some function of time. That's how we're going to parameterize it. Then rho is a function of time alone, and the total derivative is given by d rho dt equals d rho dt, the partial derivative, dx dt, remember x is just a function of t, times du dx, rho dx, sorry, like this. And if we're on a characteristic curve where this is true, if by pairing this with our original PDE, if dx dt equals c of rho, the wave speed, then d rho dt equals 0. That means rho is constant along these characteristic curves. This defines the characteristics. Because it's constant on the characteristic curves, they must be somehow an evolution of the initial condition. So we have on the characteristics rho I guess it's x t equals rho x naught, right? Because it's now x of t at 0 equals f of x naught, right? So whatever our initial condition is, it's got to just evolve along our characteristic curve. We can take this and plug it into our characteristics. So we can write dx dt equals c f of x naught, right? Even though we don't know what c is, we know this thing's constant, so we can actually integrate this with time. We can find that our characteristics are thus straight lines with slope given by this or inverse this, depending on how you think of your characteristics. If you think of characteristics x as a function of t or t as a function of x. So there's a couple of different cases you can get depending on your initial conditions. If your initial conditions are nice and beautiful, you'll get characteristics that are also nice and beautiful. Right? You can get this constant characteristics everywhere. Or constant slope characteristics throughout the domain. There's also the possibility that your characteristics look like this, right? Which is called a fan. So we know what's going on out here, but there's actually extra stuff going on in here. And then the final one, these are each individual values of x naught, by the way. The final one, which is shocking, is characteristics that intersect. Right. So these are intersecting characteristics. And this has a shockwave solution. So if you've got fan-like characteristics or shockwave solutions, you actually need to modify your PDE problem. You don't actually have enough information to solve the PDE everywhere immediately. You actually have to add some extra stuff to your problem. However, that's a bit of a review of traffic modeling problems. And the types of behavior that you can get with the solution, depending on what that wave speed happens to be, and depending on your initial condition. So this, or this happens depending on how your wave speed and your initial condition interact to give you the slopes of your characteristics.